On the average Greater Puget Sound day, and the aircraft that most of us fly, operating out of the airports that most of us operate out of most of the time, it will probably not matter much if you do not know your cruise speed turn diameter, or the induced power requirement for a 30 or 45 degree bank turn. And in the little canyons that we have over here to the east of us that we go in and out of at 1,000 feet in MSL, even being in the wrong canyon position on the average calm day isn't going to make much of a difference. Your threshold true airspeed down here at Boeing Field or Arlington or even over here at Auburn, where I'm out of, isn't going to make much of a difference. If you get your takeoff performance figures off a little bit, or you don't know your VY or VX exactly for that day, because it does change on a day-to-day basis, probably not going to make much of a difference. If you're demonstrating a short field takeoff and you use the wrong flap setting, unless you're taking a check ride, that's probably not going to make much difference either. Not much risk there involved. If you don't understand your climb gradient going out of most of these airports around here on the average day, once again, it's not going to make much difference. And if you use the wrong short field takeoff technique when you're practicing, once again, unless you're taking a check ride, nothing catastrophic is going to happen. But if you are operating in a true high density altitude environment and you don't know every single one of these, it can kill you. If you're going into a high density altitude environment, you need to know every one of these cold. The lack of knowledge of these factors kill pilots over and over and over again. Most people that I talk with informally believe that the most common factor involved in aircraft accidents is VFR into IMC. And in certain parts of the country, especially back east, that is true. But in the greater Pacific Northwest, meaning Washington, Oregon, Idaho, Montana, Wyoming, and Utah, the single most commonly reoccurring factor by far in fatal aircraft accidents is a lack of understanding of the aerodynamics involved in operating in the high-density altitude environment. If I had somebody put $100 in my bank account every single time I had investigated an accident where density altitude was a primary factor, I could have retired years ago. As Scott mentioned, I'm going to call not knowing any one of these. These are the 9 deadly sins, lack of knowledge of any one of these specific items. And we're going to talk about each one individually, and we're going to go through it. We're going to show you why and how it can kill you. The first deadly sin: not knowing your density altitude turn diameter. Now, I don't mean to insult anyone, but I want to start from the beginning to make sure we're all working off the same sheet of music here. Sea level, about 55 degrees. With 150 indicated, ignoring calibrated and equivalent airspeed, we're going to have approximately 150 true, okay? 150 indicated, 150 true. Then we go to that location where the guy was doing the air show, 8,000 feet, 95 degrees, still 150 indicated, and our true airspeed now is 180 knots. Not 150 knots, 180 knots, with exactly the same indicated airspeed. That's the source of the problem that generates the deaths from pilots that do not understand their turn diameter. Higher true airspeeds for the same indicated airspeed at a higher altitude. Now, we need to determine our turn radius. That's the formula for it. The radius equals your velocity in knots squared over a constant of 11.26 times the tangent of phi. Phi is the bank angle, so it's 11.26 times the tangent of the bank angle. Now, in all of the problems we're going to talk about tonight and all the issues, I'm going to use 45 degrees of bank. Now, you mathematicians and engineers out there, why am I using 45 degrees of bank? I heard it out there. Correct. I want to make everything as simple as possible for myself, and the tangent of 45 is 1. So now we've reduced our formula to 1 times 11.26, or in other words, just 11.26, into our velocity squared. Now let's take a look at what that looks like at sea level at 150 indicated, and at 8,000 feet at 150 indicated. Sea level, 150 indicated, 45 degrees of bank. 11.26 into 150 squared, we get 1,998 feet as a turn radius. We're going to call it 2,000 feet. Okay? At 8,000 feet, under the conditions that we defined earlier, still 150 indicated, still 45 degrees of bank, turn radius 3,240 feet. About 1,200 feet more at exactly the same indicated airspeed and at exactly the same angle of bank, because we have a higher true airspeed. But that's only half the problem, because your turn radius will only get you halfway around going back out of the canyon, right? Here's your turn radius from here to here. So this is the turn radius taking you around to 90 degrees, but then you got to go all the way around and get back out. You need to go 180 degrees. So it's not the turn radius we're concerned about, it's the turn diameter. It's the complete distance across that valley going in, making the turn and coming back out, 180 degree turn. You need to know what that turn diameter is going to be at the altitude and airspeed that you are flying at. Let's take a look. Okay, we already said that at sea level, 150 indicated, 45 degrees of bank, our turn radius is about 2,000 feet. At 8,000 feet, 45 degrees of bank, 150 indicated, our turn radius is 3,240. But our turn diameter is about 4,000 feet at the sea level and about 6,500 feet at 8,000 feet. It's going to take us almost 2,500 feet more across that canyon to get in there and turn around and come out at 8,000 feet than it does at sea level. And the problem is that all of us have a mental picture for flying at sea level. We all know what it looks like when we enter a pattern out here. We all kind of know how far away we have to be, because we know with the bank angle that we're going to use how much of a turn it's going to take. Even if you wanted to make just a complete 180 degree turn to go back to something or to look at something, you have a visual picture. You kind of know where you need to start that turn. This is what you're used to at sea level. You got your little 5,000 foot wide canyon there. You come up the canyon here at about 200 feet off the side of the canyon. You get up in here and you go, oh, it's getting a little tight, I'm getting uncomfortable, I'm turning around, I'm going back out. You do your 4,000 foot diameter turn, you got 800 feet left over on the other side of the canyon. Now, we go to 8,000 feet, the same stinking 150 indicated, the same stinking 45 degrees of bank, and there's where you end up, right there. Got a new turn radius. It's from this dot over to here. You start your turn, get a little bit past 90 degrees, either run into that wall over there, or what I usually see is that you steepen it up at that point, load it up, stall spin, right down into the side. That's where I get to see your aircraft, and possibly you for the very first time. You do not want to be one of my clients. Please learn what your density, altitude, turn diameter is at the speeds that you're normally going to be flying in that type of country. Okay? You can figure it out. It will kill you if you don't know it. Make sense? If I were to stop right there, I could be responsible for at least a few crashes and maybe the deaths of some other pilots. Because when people hear this, they say, well, that's all right. Because I've heard about guys that do just the opposite. They know they can go up into that canyon and slow that thing down. And of course, if you slow it way down, it really has a very small turn radius, a small turn diameter. You can get in there, slow that thing down, put in 20 degrees of flaps, and get that thing around in no time at all. I've met a lot of these guys. Because they did not know their density altitude induced power requirement for a slow speed turn, okay? Their induced power requirement for a slow speed turn. When we got our private pilot's licenses, they did not show us everything that we needed to know. They showed us these charts. We're all familiar with these. The top one shows the increase in the stall speed as the bank angle increases. And it's not even a very exciting chart until you get up here about, you're up there about 35 or 40 degrees of bank. Then you start getting 10, 15% increase in stall speed. So that gets your attention a little bit, but it's not all that exciting. This one is even less so. We all know this one. The increase in the G load as the bank angle increases. The line stays almost flat until you get to about 30 degrees of bank. 40 degrees of bank, you get about another half G in there. You got to get clear up to 60 degrees of bank to get 2 Gs. Not real exciting stuff. How many of your instructors showed you this one? On the left-hand side, we've got the bank angle, just like before. In the center column, we have our load factor, which is the same as that other graph. Shows the same thing. You got to get clear up to 60 degrees of bank before you get the load factor of 2. But what's this thing over here on the right? Percent increase in induced drag from level flight. Now, they didn't show me that one when I got my private pilot's license. 15 degrees of bank increases 7%. Yeah, that's not a big deal. 30 degrees, 33%. Well, that's a little bit of a deal. 45 degrees, my induced drag increases 100%. 60 degrees of bank, it increases 300%. Well, this is a little bit more exciting chart, okay? Let's talk about what this is going to do to you. Let's talk about what this is going to do to the person who tries to turn around slow in that canyon. Okay, we're going to go back to a chart that all of us know. Most of us refer to that as the L over D max chart or the total drag chart or something like that. We're all pretty familiar with it. The top line is the total drag. The parasite drag shows that as you increase airspeed, parasite drag increases significantly. And it shows as you decrease airspeed, induced drag increases significantly. And it shows us where the L over D max is, where the lowest point of drag is. If we go any faster or any slower, the total drag increases from that point. But because we're going to be talking about a low speed turn where induced drag is important, we're going to take some of the lines out of this chart. Okay, same chart. I took out the L over D max part, and I took out the parasite drag, and all we have left is induced drag. Something you might notice here is that we've called this chart by its wrong name. We call it the L over D max chart, or the total drag chart. I didn't notice for years that it's not really that. What does it say on the top? Drag or thrust required chart. I never thought about that. But remember the little picture? The lift up here has to equal the weight, and the thrust over here has to equal the drag. And I go, wait a minute, now we're talking about increasing induced drag by 100%. There's something going on here. We're going to have to increase our thrust to make up for this. But just how much? That's what we need to know. Okay, let's start out at a high airspeed where induced drag is a very small portion of the total drag. We're up here at, I'm going to use knots. It says miles per hour, but we're going to use knots. We're up here at 180 knots. Here is our total drag. The portion of the total drag that is made up of induced drag is just this little portion down here. Matter of fact, I've moved it off to the side as a unit so you can see how big that unit is as compared to that whole total drag. So that chart, the one I showed you before, it showed that at 45 degrees of bank, we increased our induced drag by 100%. We doubled our induced drag. So I'm going to take this amount of induced drag that's here and take it up here and just set it on the curved line here and see how far up that would have taken the line. And it would have taken the line up to that dot. The total drag line would have increased that much. In other words, at 180 knots, at 45 degrees of bank, the total drag is going to be increased by only 6.7%. Not very significant. That's why when you're at cruise airspeed and you go into a bank, it really, we all know we have to add little power, but not that much. But we all know from experience, when we slow it way down and go into 45 degrees of bank, it takes significantly more power to maintain our altitude. Like so. We've slowed down to 65 knots. At that point, the majority of the total drag is made up of induced drag. As a matter of fact, I've done the same thing here. It's got the unit, that's one full unit of induced drag. I move it out here to the side so we can see how big it is. Move it up here and bring it back in on the line to see how far the line would go up. The total drag line goes up to there. At 65 knots, the total drag has increased 79.3% when the induced drag is increased 100% because of the 45 degrees of bank. Now, when's the last time you were flying at 8,000 feet at about 70 or 80 degrees outside temperature and had 79% left extra power, extra thrust in that engine of yours? We've all done this. We've all seen it, either as a student or some people that are instructors. You've gone up out here and you go up to 2,000 feet or so and you practice slow flight and you put down flaps, whatever you use for that in your airplane, 20, 30, 40 degrees of flaps, and then you stabilize the aircraft and you have the student or yourself do some turns, do at the beginning, 15 degrees of bank, and then you take them up to 30 degrees of bank and they're all scared and you're kind of nervous too, and you get up to about 30 degrees of bank, and it's the first time they've done it, so they're a little sloppy, and they get over to 35 degrees of bank. What happens to the power? You got to firewall it just to keep the thing from slowing down and from descending, right? Third deadly sin. Oh, I love this one. Not knowing your density altitude best canyon position. Like I said when we started, when you're down here, just playing around over here to the east of us, and you're at 1,000 feet, on a cool Seattle day, we don't really get, except like today, we get some winds, but normally we don't get much. It's not going to really make a big difference if you're in the wrong position in the canyon. But if you are in a true density altitude situation, it is going to make a big difference. I bet you 95% of us at least have seen this diagram before. This is a good diagram. I've seen it in a lot of different places. I copied that one directly out of the AOPA Air Safety Foundation mountain flying book, and if you don't have this, if you're a member of AOPA, you need to get it. If you're not a member, call them and find out how you can get it anyway, okay? It's their mountain flying book. It's a great book. It tells us where to fly in a small canyon. Now let's get a mental picture of this canyon. It says, flying alongside the ridge line results in downdrafts for the pilot of aircraft A, okay? Aircraft B might escape the sinkers, but has little maneuvering room on either side should a course reversal become necessary. So it's a pretty thin canyon, right? You can make it from A to B or B to C, but if you're at B, you're going to have a real hard time turning in either direction. Pretty thin. Pilot of C gets free lift from the upslope airflow and maintains an into the wind escape route. So you fly in C, and when you get in trouble, You turn around and come out the other side, and everything turns out hunky-dory, right? Let me show you something here. This is the classic case of you cannot have your cake and eat it too. Okay? Pilot C gets free lift from the upslope airflow and maintains an into-the-wind escape route. Okay, he's over here in C, things aren't going well, he turns around, and he comes out over here in A, in the into-the-wind escape route. But wait a minute. In the sentence before that, they just called it an area of what? Downdrafts and sinkers. You think when you went over to fly in Area C that all of a sudden Area A didn't become an area of downdrafts and sinkers anymore? And you're only going to turn around when things get bad in C, right? As long as things are going good in C, you're going to keep going. So now things are starting to get bad. So where do you turn? To A, the worst place yet. Into sinkers and downdrafts. About 5 years ago, I got called to Yellowstone Park. There was 3 air coups, which are not, real good high-altitude aircraft anyway. Neat little airplanes, but, not at 8,000 feet and 90 degrees. And these 3 air coups were going through a pass up there, and they were following in trail of each other about a mile apart. And they were doing the right thing according to this chart. They were flying over here at sea. And it was pretty windy, and they were getting a lot of updrafts over there. Performance was pretty good. And as they started getting to the pass itself where it narrowed, the performance was pretty good. They weren't worried about that. They were getting a lot of updrafts. But it got so turbulent that the guy said, I don't think so. I don't think we should go through here. So he made his turn, and he came out between B and C over here. When he got about to B in his turn, he started to sink. The further he got past B over to A, he started to sink even more and more. And those other 2 guys in those trailing aircraft are watching him as he descends into the top of the tree. The wings are ripped off the aircraft, and it explodes right in front of the other 2 air coup pilots. He was killed. The only thing he was able to do was transmit something about downdrafts. That's exactly what he did. He went from C into A, thinking that was a good area to turn around it. It is not. Do not go into a canyon that you cannot fly in position C and still turn around way, way, way over here to the right-hand side of B. If you end up at B or over to that other side, you are flying into that area that they told you to avoid in the first place. I can't tell you how many people have been killed by not understanding this chart. That make sense? Okay? That's a real insidious one. We don't think about that. We end up going back out the other side. Or at least we get halfway out the other side. Not knowing your density, altitude, landing ground speed. Okay? Your landing ground speed. One of those aircraft that I own, the one I fly most often, is a 1951 Cessna 170. And so I took some of the figures from my operating handbook. And a situation similar to that one where we saw the guy in the T-34. In other words, we're at 8,000 feet, 95 degrees, winds 10 gusting to 18, and they're variable winds. They're all over the place. And my book says you should use an indicated airspeed of between 70 and 75. And I'm up there in the mountains, and it's really bumpy and all that kind of stuff, and I'm going to use the extra 5 knots for mama or the spouse, because that's just the kind of thing you do to be safe. So I'm using 75. But remember what we talked about earlier on that very first chart? 75 indicated at that altitude and that temperature is 90 true. So if the wind, as it gets sort of variable in there, is a crosswind or is just not blowing at the point that I cross the threshold, I'm coming across the threshold at 90 true, 90 miles an hour ground speed at that point. But then I remember something back from my training when I got my private pilot's license, and it said something about adding half the gust factor. And I'm not sure, once again, I'm thinking, oh, gee, it's half the gust factor. What's that? Well, is it the difference between 10 and 18, 8 knots? Or is it the difference, or is it just the 18? And no, geez, I don't know. That's why I've got the question mark, so I don't know. And that's what happens to a lot of pilots. They get up there and they go, I'm not sure if the gust factor was the total gust or if it was the difference between the steady state and the gust. But once again, I'm going to play it safe. We're up here in the mountains. We're getting bounced around, so I'm taking the whole 18, because that's only half of that. So half of 18 equals 9, so another 9 indicated. Oh, wait a minute. 9 indicated is 11 true. So I got 90 knots of true just from going 75. I got another 11 knots here for using my gust factor incorrectly. I come over the threshold at 101 miles per hour. Now, how far do you think my 170 will float at 101 miles per hour? Try it. Just try it right down here at your favorite hometown airport. Watch your flaps, your flap speeds, but this is, what I usually use 70, or 65, when I'm doing, so I'm about 30 miles an hour higher than I normally would be. If your airplane is a miles per hour airplane like mine is, try that, 30 more, or 25 knots more, or something like that, and come over the threshold and see what it gives you. And then you'll know what you'll be facing the next time you try to go into that situation in a high density altitude environment. And somebody in the last seminar says, well, yeah, fine, but what can you do about it? Well, not go there, The next killer. Not knowing your density, altitude, takeoff numbers. I'm going to show you now the chart that causes more trepidation and anxiety on the private pilot test than all other questions combined. Because the test question says, your gross weight is 2180. Oh, damn. You have a headwind of 3 knots. Uh-oh. They got them broken down in 5-knot increments. Well, we can do this. We can do this. And we're at 6,700 feet pressure altitude. Okay. Well, they got a 5,000. They got a 7,500. Oh, boy. And it's, what do we got here? It's 80 degrees. Well, they got 41 degrees and 32 degrees. Oh, wait a minute, here's the thing. Increased distance 10% for each 25 degrees above standard temperature for a particular altitude. Oh, okay. What is the standard temperature for 6,700 feet? Oh, boy. Okay, so then we've got, but this is a mountain strip and it's dirt. And there was a little shower that afternoon, and it rained, and it's wet. And so we've got mud. Not deep mud, but just kind of a muddy dirt strip. So let me see the mud factor. Right, oh, here we go. Increase, no, right here. For operations on dry grass, well, that's close. Increased distance, both ground run and total to clear 50-foot obstacle. I got a 100-foot tree down there. By 7% of the total to clear the 50-foot, oh, shoot. What do you do with it? You throw it out. How many pilots use that chart? Then nobody uses it. They've got the slightest idea. If I were to give that chart out in this class and have everybody work the problem, we'd get, what do we got here? 200 different answers. The problem is that every one of those answers can kill you. Your life depends on those answers. So wouldn't it be nice to have something that would tell you the answers exactly? How many people have one of these? Let me see some hands. Top comp, it's called a top comp. See two hands, two hands. Top comp, takeoff, performance, computer. Sporty's Pilot Shop, 1995, save your life. And I like it because it's made out of cardboard and you just push the little levers, you know. It's very easy to use. And it will give you the answers. This is what it looks like in black and white. It has a card that slips into the top of it. It has one side for a fixed pitch propeller, and the back side is for a constant speed. So I've got my 170 fixed pitch propeller in here. Over here, you slide this card up and down, and then over in this window, it'll set the temperature. That's the first thing you do. So I've slid this thing in here at 90 degrees. The very first thing you do after that is you go over here to this right-hand side to the percent of your sea level standard day rate of climb, ROC. And you go to your pressure altitude. And it'll tell you what the percent is going to be of your normal sea level rate of climb. You're at a field. In the airport directory, it says it's at 5,000 feet. How do you determine what your pressure altitude is so you can enter this chart? I see somebody doing it. Okay? For those that don't know, you set your altimeter at 2992 and just read what your altimeter says. That is your pressure altitude. That's what you need to go on here. So depending on the barometric pressure that day, if you're at a 5,500 foot field, the pressure altitude may be 6,000 or 6,500, but you get your pressure altitude. 2992, read it off the face of the altimeter. Come over here to our sample, 8,000 feet, and you know, they don't even, you can see there, they don't even have the courage to put a number down there because they know it's going to be so bad. At sea level, okay, 90 degrees at sea level, it's 87%. At 2,000 feet, it's 70%. 4,000 feet, 52%. 6,000 feet, 27%. 8,000 feet, we don't want to be sued. So there's nothing down there. Okay, right there, rate of climb. The next thing you do is that you move these little cardboard slides, okay? Anybody that's been in the military or possibly old person with, you know, old weight and balance on a transport category aircraft has used something similar to this with the little slides. Each one of those slides has a cursor arrow, and it points to the slide above it. So let's walk through a sample here. We've already set our temperature, and we are going to be at 8,000 feet. So we take the cursor just below the pressure altitude field, and we set it below the 8,000 foot, okay? Then our runway is going to be a grass runway. So we take the arrow below that. It's on the runway slope, but it's the cursor for the next higher slide, and we set it at grass, okay? Now we want to do the runway slope, so we take the next lower cursor, which is the wind one, but it goes up to the runway slope, and it's at a +2, okay? 2% up slope. And then for our wind, we have a 5-knot headwind. There's a cursor there. And for our gross weight, 80% of our max takeoff, of our max gross weight. Now I love this slide. Look right there. What does it say? Percent of gross weight? Hey, this is real life. How many of your pilot operator handbooks have in them 120% gross weight performance takeoff figures? But this does, okay? But we're at a high altitude field, we're going 80%. Put the cursor there at 80%. Then we go down, the cursor kind of turns around, and we've got different sample aircraft here, 180, 182, 152, Bonanza, what's this, arrows over here is Archer, 172, Skyhawk. My 170 at max gross weight takes off at almost exactly the same distance as a 150 does in max gross weight. So here we've got about 730 feet. So I just use the 150 or 152. But if it's not marked on there, if the aircraft that you fly is not already marked on here, then you just go into your handbook and find out what the sea level standard day max gross weight takeoff distance is, and you just put a little dot there on that slide, and then it'll always line up. Okay? So it shows me under all these conditions that I will not be taking off at 730 feet, but I'll be taking off at 15, 16, 17, 18, 1900 feet. That is a good little tool. 1995. No, I don't get a commission. I think I should. But it's the only thing I've seen. The FAA used to have a Denault computer, density altitude computer, but it didn't have all this stuff on it. This thing's got all the instructions right on the back. The batteries never go dead. It's a great little device. One of my other airplanes is an Aeronca Chief, and it's not on here. So on mine, I just have a little dot down there, because I know what the standard sea level, takeoff is for that. So great, great little computer. I haven't seen anything else like it. If I knew of something, I would tell you about it, but it's the only thing like that I know. Okay? You need to know precisely your takeoff performance figures in high density altitude environment. And by the way, this thing answers the old runway slope tailwind headwind question. Do I go downslope with a tailwind or upslope with a headwind, or what do I do here? This answers it. Just run it both ways. This kills more pilots than all the rest of them combined. You need to know your density, altitude, Vx, and Vy speeds. I will bet you that at least 95% of the people here right now, without looking in their handbook, know their Vy speed, their best rate of climb speed. But I will also bet you that the majority of us don't know how it changes as we increase in altitude. And the reason I can say that is because of the question I just asked Scott, because he had that little, at the end of that little test that was given out, another speaker gave some kind of a test at the end of a presentation, and Scott added a question, which was, what happens to your Vy speed as altitude increases? And every one of us needs to get that right if we're going to operate in a high density altitude environment. But unfortunately, 33% of the crowd got it right. 66% got it wrong. And this sucker will kill you. You need to know this one. This chart is a little bit confusing because we're used to charts that when they have a speed on it, the speed starts over here, and as it goes across, it gets higher. On this chart, it gets lower. So you can see 73, 72, 71, goes on down, 61, 50, 60, 59, okay? So it is a little backwards there. But knowing that, you can see that as altitude increases, your Vy decreases. As altitude increases, best rate of climb speed decreases. One more time. As altitude increases, best rate of climb speed decreases significantly. By the way, Vx, best angle of climb speed, increases. That's what it shows here on the chart. And they come together up here at your absolute ceiling. L over D max again. If you go a knot faster or a knot slower, you're going to start to descend. You're not going to fall out of the sky, but Start to descend. Okay. How much does it decrease? How much does Vy decrease as altitude goes up? Well, let's look at some handbooks. 182Q, 2950 gross weight, best rate of climb speed, sea level 78, 2076, 4075, it goes right on up, 73, 72, 71 at 12,000 feet. An older 182, 56 or 58, max gross weight, okay, sea level, best rate of climb speed, 89. They've got it in miles per hour, which is exactly what mine is on my 170, 89 miles an hour. I use 90 because I can't see 1 mile an hour. But 89 at sea level, 5,000 feet it's 85, 10,000 feet it's 81, and if you happen to have a density altitude up here around 15,000 feet, it goes clear down to 77. But we'll stick here at 10,000 feet, 81. 8 miles an hour slower. Now, if you don't think that makes a difference, go out here sometime and take off down here at sea level at the best rate of climb speed that you normally use. You know, in this example, let's say it was me, it was 90 knots. And then lower the nose to accelerate so you are, as in this case, about 9 knots or so, 7 or 8, 9 knots too fast. And look over at your VVI, look at your vertical velocity indicator and see how much your rate of climb decreases. It will be significant. If you are not climbing at your best rate of climb speed, your rate of climb will decrease significantly. Do you think that's something you want to do in a high density altitude environment? Now, that's only half the story, because it's not only the fact that as the altitude increases, the best rate of climb speed decreases, but there's something else that decreases it even more. What is it? Temperature is going to decrease your rate of climb, but your weight, your aircraft weight, okay? Let's run through here again. Gross weight, 89 at sea level. We go over to 10,000 feet, it's 81. Now let's drop down at the same 10,000 feet to the 1950 gross weight line and come across. Drops from 81 down to 76. And what do we do when we go into high density altitude situations? We unload the aircraft, we make it as light as we possibly can. So it's quite likely that you won't be going in there at 2550, you will be going in there at 1950. And if you fly out of there at 89 instead of 76, 13 knots difference, 13 miles an hour difference, your rate of climb is going to decrease significantly. You will not make it over that ridge that's 4 miles off the end of the runway. And that's when I get to visit you. Okay? Remember that. As the altitude goes up, your best rate of climb speed goes down. Go home and look in your book and find out what it is and how much. You need to know that. Okay? Do you know the flap setting to use for a short field takeoff in your aircraft? Do you know it for sure? 10 degrees? Is it 20 degrees? Is it 0 degrees? Not specified in yours? Oh, that's good. Well, this is out, this isn't out of mine. It's out of Eric's. This is a B model 170. It shows here that with flaps up at sea level, takeoff, run, and this includes clearing a 50-foot obstacle, is 1460. With 20 degrees of flaps, it goes down to 1230. So it makes a significant difference having those flaps in the correct position. And even more so because with flaps up, the ground run is 40% of this total distance to clear the 50-foot obstacle. And with the flaps at 20, the ground run is only 38% of this shorter total distance to clear the obstacle, okay? makes a big difference when you're up there at a high density altitude, especially when you start getting up into these dangerous areas where you have 80 degrees and 7,000 feet, like some of these situations we were talking about. So make sure you have the correct flap setting in there when you get into those density altitude situations. When you're up here in this place, that little block right there, you want to make sure you got your 20 degrees of flaps in. Right? Wrong. I took the liberty of using some whiteout on that last chart. See the little star over here? What does the note say down there at the bottom of the page? In this area, the use of wing flaps will increase the takeoff distance. On every one of your aircraft out there, there is some altitude and some temperature at which the flap setting that they tell you to use will increase the takeoff distance. And you need to find out what that is. Now, us lucky old guys, or lucky guys, that fly old aircraft, back before attorneys were concerned about having too many things in the operator's manual, have a little black area with a star, and it tells us right there, don't use 20 degrees of flaps in those situations. But you're not going to find that in your books if you're flying something modern. I've only been able to find it in two aircraft operating manuals, and they were both old aircraft. But it's in there somewhere, and if it's not, then you need to call the manufacturer or do something, take some action. Because if you're up there, I'll tell you, if you're up there at 8,000 feet and you've been in 20 degrees of flaps, you're going to have big problems, okay? It's a killer. Right into the trees off the end of the runway, okay? Seems like there's no end to this stuff. Did they not teach you everything you should have been taught at your private pilot's class? Not knowing your density altitude climb gradient. Okay, this is not your rate of climb, this is your density altitude climb gradient. Rate of climb is feet per minute. Climb gradient is feet per nautical mile. Big difference, and it'll kill you. It almost killed a really good friend of mine. He had a J3 Cub with a 90 horsepower engine in it, and he knew that when he and his daughter were in that aircraft and it was full of fuel, and my wife and I were in our aircraft and it was full of fuel and a little baggage in the back, that our rate of climb actually ended up being about the same. And he'd always wanted a 170, so he went back east and bought one. And then he brought it back through Colorado, and he landed at a high-density altitude field. And he knew that he would have the same rate of climb in that 170 as he had had in his J3 Cub with the 90 horsepower, and he'd been into some high-altitude fields, so he knew it wouldn't be a problem. But it was, because he did not understand his climb gradient in the 170. They took off. And as they tried to climb over a ridge, a mile or so off the end of the runway, they didn't make it. They were both injured, not real seriously. They were able to get out of the aircraft, and just when they did, it caught on fire and burnt up. I haven't seen him in a few years, but when I left Southern California, from the time of that accident until the time I left Southern California, he would never get in a 170 again. And I've owned 3 of them, and they're great airplanes. It's not the airplane, it is not knowing your climb gradient. The airport that he and I used to take off from, there was about a 1,350-foot ridge 4 miles off the end of the runway. In the J3 with his 90 horsepower engine, he had about a 700 feet per minute rate of climb, and I had about the same thing. He was climbing out at 55 miles an hour, and I was climbing out at 90 miles an hour. So although our climb rate was the same, our climb gradient was significantly different. He was climbing 764 feet per nautical mile. I was only climbing 466 feet per nautical mile because I was covering the distance sooner or quicker. So when we got out there to 4 miles, he was at 3,056 feet. I was only at 1,864 feet. So he cleared the ridge by 1706, and I cleared it by 500 feet. But in actuality, he would take off first, and then instead of going straight, I'd just kind of make this big wide loop and then come in behind him. So I had more time, and so I ended up kind of coming across the ridge at the same altitude that he was coming across it, and I would kind of catch up with him at that same time. And so that kind of lulled both of us into thinking that, well, if he goes and buys this 170, it's going to climb out the same way as his J3 Cub. Well, the rate of climb was the same, but the climb gradient was not. So he went into this situation like we've already seen a couple times tonight, where he was about at 8,000 feet and 95 degrees. There was an 8,500-foot ridge about 4 miles off the end of the runway, so a 500-foot ridge. And his J3, he knew he'd have a 200 feet per minute rate of climb, and he knew at that altitude he'd have a 200 feet per minute rate of climb in the 170. He knew he could make it in his J3, so he knew he could make it in the 170. But the difference was, he was climbing at 50. It was 55 at sea level, and he knew that he had a lower, remember, altitude goes up, VY goes down, so he was climbing at 50. And in the 170 at 85. But the difference is the true airspeed, 60 in the J3, 102 in the 170. Look at the difference there now. The climb gradient. In the J3, he climbed 200 feet per nautical mile. In the 170, at the same rate of climb, he climbed 118 feet per nautical mile, almost half. At 4 miles in the J3, he'd be at 8,800 feet. At 4 miles in the 170, he was at 8,472 feet. In the J3, he would have cleared the ridge by 300 feet. In the 170, he failed to clear the ridge by about 30 feet because he did not understand the climb gradient. Don't get yourself up into one of those high density altitude environments without knowing what your climb gradient is going to be, especially if you're in something high performance like a Mooney or something like that. Some guy will go out there and take off in a J3, you know, and 85 horse, and he'll take off and you'll watch him, and he just goes on out of there. Crap, I got better rate of climb speed than him. I know I do. But your speed across the ground is so fast that your climb gradient is a lot shallower. And he makes it over the ridge and you don't. And my pager goes off again. Okay? Know your high density altitude climb gradient. It is a killer. Hey, this is the last one. This is good. Whoops, that won't work. Okay. I've worked so many of these accidents, I can't tell you. Not knowing your proper takeoff technique in a high density altitude situation, not knowing when to use a short field technique, not knowing when to use a soft field technique, and not knowing when to use an obstacle clearance technique. What is this? I like that. I can't follow that. Well, it's either a, whatever that is, 182, I guess, landing on an aircraft carrier and trying to do aerodynamic braking, or it's the soft field takeoffs that I see practiced at most of the small airports around here when people are getting their private pilot's licenses. They pull out onto the runway and they stop. So the first thing I know is they're not doing a soft field takeoff. But then they ram the power to it and they get the thing going about, 6 knots, elevator full up, tail goes down, they lift the nose wheel to clear 3-foot stumps. Now, how many of you, even though we shouldn't do this, but many of us have, how many of you have ever tried to lift the nose wheel of a 172 or 182 off the ground? You got to go back on the tail and try to, lift it up just for, whatever reason. I hope you don't move it around that way, but I know some of us have at one time or another. I mean, I can't do that just by pushing down on it. I have to lay across the top of it to get that nose wheel to come up. Now, this guy's taken off with the total weight of this aircraft, but now he has just added all the additional weight that it takes to deflect this stabilizer down to lift that nose wheel off the ground. So this aircraft weighs considerably more, a couple 100 pounds more, than it did when it rolled onto the runway. And now that weight is not distributed on 3 wheels, it's all distributed on 2. And when you go and watch this takeoff, everybody else is taking off, just their normal takeoffs, going on their trip for that day, and they're 182 or 172. They do their normal takeoff, and zoom there, they go, they break ground at 900, 1,200 feet. This guy's just chugging along down there, 1,800 feet, 2,000 feet, it won't accelerate. He's got all that aerodynamic load from it being up like that. He's got all of that extra weight. He's got the wheels, all that weight just on those 2 wheels. And then he goes and does it on terrain that he or she thinks is soft, but it is not. How many of you have landed over at Capella State on the beach? That is not soft. I mean, if you get over there in the dry, deep sand, that's soft. But where it's damp and hard, I mean, I've ridden my bike on it, and I've landed on it, and it's not soft. You need to use soft field technique to take off over there, even if it was short. There's no stumps to hit. How many of you landed up here at the Easton State, right up here in the pass? It's very rough at times, but it is not soft, and there are no 3-foot stumps. You do not need to be using this type of technique up there. Had an instructor and a student and another person that was riding along with him have an accident up there a couple years ago, and I got to talk to both the student and the instructor on the cell phone about 5 minutes after it happened. And basically that's what they did. They used this short field technique, they used this soft field technique on a field that wasn't soft, so it made their takeoff roll a lot longer, and then they transitioned from that extra long takeoff roll to VX to clear the trees off the end of the runway, and got it up on the edge of the prop and behind the power curve, and the instructor was smart enough to know at that point that they weren't going to make it, even though he was above the trees, but they were not going to make it. So he nosed it over and cut the power, brought it back down on the runway, and went into the trees at the end of the runway. A lot of times that ends in fatalities. Do not use soft field takeoff techniques when you don't have to use them, especially in high density altitude environment, because it increases your takeoff roll significantly. If you're going into some place that you know is soft and it's a high density altitude environment, maybe you shouldn't ought to be there. Second takeoff issue. Don't use VX, best angle of climb speed, when VY, best rate of climb speed, will do. I gave a flight review here a while back and went over to Thun Field, and we took off, and this person rotated and went right to VX. We were taking off on 3-4. And first of all, I couldn't see, and that really bothered me. And secondly, we're just sitting there at VX and sometimes a little bit below VX. And I said, what? Well, actually, we flew on around the pattern, we landed, and I took the aircraft, and as we took taxi back, I said, why did you use VX? To clear the obstacle. What obstacle? The trees. They're down there at the end of the runway. Well, yeah, what is it, a 3,400-foot runway or 3,600-foot runway or something like that, and 1,000 feet off the end of the runway, there's some 100-foot trees? And yet this person used VX. You don't need to put yourself into that critical environment unless you really need to put yourself in that critical environment. If VY will do, use VY. Okay? Don't be using VX unless there's really an obstacle to clear. And I'll tell you, if you're going into an airstrip up here in a high-density altitude environment, and VY won't get you over the obstacles, and only VX will, I ain't going with you. Okay? Because If that field is a little softer than you thought, if the wind shifts 45 degrees, if the compression isn't quite what it should have been when all those tests in the operator's manual were done way back in that stripped down, non-painted, no radios airplane, then it's not going to do what it says it's going to do in the book. There are some experienced mountain pilots that go into places like that and have to use VX to get out of there, and that's fine. But for the average everyday pilot, if you're going into some place that needs VX, you need to make sure you've got a lot of experience, have taken a mountain flying course, and have worked up to that. Okay? Don't use VX when VY will work, and I recommend don't go into a place where only VX will work unless you have the experience to safely do it. I have more than enough job security. I have more accidents than I can handle. I don't need more. The last thing, don't combine soft field with either short field or obstacle clearance. Just don't do it, okay? Because of what we talked about earlier. Your takeoff roll is going to be significantly increased by using soft field techniques. So if you know you're going to have a short field, it better not be soft. And if you know you're going to have an obstacle and have to use VX, or even not use VX, but there's an obstacle, fairly close in there, it better not be soft. Because as soon as you start using these soft field techniques, all your performance takeoff data goes out the window. Who knows how much longer it's going to take you to go down and accelerate and get off that runway? Don't combine them. I hope you go home this weekend and learn all of these things about your aircraft. You need to know your turn diameter at a high density altitude cruise type speed. You need to know the induced power requirement for your aircraft in a 30 and a 45 degree bank up at 8,000 feet. You need to know the correct canyon position. You already know it now that we've talked about it. You need to get that picture in your mind. You cannot go into that little canyon that they show in the book here, because you're going to turn around and come out in the bad area. You need to make sure you know make sure that you know how to figure exactly what your threshold true airspeed is, which if there's no wind is going to be the same as your ground speed. You need something besides that cockamamie chart that's in the book to figure your actual takeoff performance figures, something like this. You need to go into your books and figure out what your VY and VX is as your altitude increases, especially VY. That's what most of us are using. You need to know what your short field flap setting is, and you better know where the reversal point comes where you can't use them, where it's going to make your takeoff roll longer. You need to figure out your climb gradient. Take the sample of, look at your in your manual and figure out at what altitude you're climbing at 200 or 300 feet per minute, and then figure out what your true airspeed is going to be, and figure out what your climb gradient is going to be. Okay? How many feet you're going to climb across the nautical mile. And just think a little bit about what we said tonight about, those different things about soft field takeoffs and combining them and all that type of thing, okay? If you do that, maybe we've saved some lives in here tonight. Maybe I'm not going to have to come out and meet you professionally. I don't want to have you as a client. I'd be glad to fly with you, but I don't want to have you as a client on the side of a hill.